Welcome to the Chapter 7 Part 1 notes. This will be 7.1, 7.2, and 7.3. Starting off with 7.1 and 7.2 together, our objectives are to write ratios and solve proportions, and also to identify and apply similar polygons. So as a reminder, we know that a ratio is a comparison of two quantities by division. So if we are comparing A and B, we can say the ratio of A to B, which also means A to B. So we can write it as a fraction or in ratio notation with a colon. When we compare ratios, that is a proportion, and a proportion is an equation. So there has to be an equal sign for it to be a proportion, and it states when two ratios are equivalent. So here are some examples of proportions. If we wanted to solve for x in these proportions, there are a couple of ways to do it. The most commonly used way is what we call cross multiplication, which means we're multiplying really by an LCD. We're multiplying by all of the denominators. So we're going to multiply x times 5 to get 5x, and 4 times 6 to get 24. And then to solve for x, we need to divide by 5 on both sides. And so we get x equals 24 over 5, which, if we need it in decimal form, is 4.8. Okay, we can use that even if there's more than one variable present, as long as it's the same variable. So we've got two copies of x here. Again, we're going to use cross multiplication. So 3 times x plus 4 in parentheses equals 9 times x. Distribute that 3. 3x plus 12 equals 9x. Minus 3x. 12 equals 6x. Divide by 6, and x equals 2. Okay, so that's solving proportions for x. So if we want to look at our first example here, the bonsai bald cypress tree is a small version of a full-size tree. A Florida bald cypress tree called the Senator stands 118 feet tall. What is the ratio of the height of the bonsai to the height of the Senator? So this is going to be telling us how to set up our ratio. Bonsai 2 tells us where the colon or the fraction goes. Senator. So because bonsai is said first, bonsai is our numerator or our first number. Okay, so we're given a picture here of a bonsai tree that's 15 inches to the senator tree, which we are told is 118 feet tall. Notice my units here, inches and feet, they're different. We need to first convert them to be the same unit. So if you recall, there are 12 inches in a foot. So that means 1 foot is 12 inches. So to convert from feet to inches, I have to multiply this by 12. And so we get 15 inches. 118 times 12 is 1,416 inches. And then we want to see if we can simplify it. So remember, another way to write this ratio is as a fraction, 15 over 1,416. And we can simplify that either by dividing by any common factors, or we can do it in the calculator. And we will find that this simplifies to 5 over 472. And so to write it back in ratio form, we would do 5 to 472 inches, because now both units are in inches. Another type of ratio is called an extended ratio. And that means we're not just comparing two values, but more than two values. And this is what we'll be using for a lot of our new information for this chapter, comparing triangles. So triangles have 3 sides, so we will use extended ratios a lot. So in this example, the lengths of the sides of a triangle are an extended ratio 3 to 5 to 6. So that means if I draw this triangle, if this side is the shortest side, it's 3 times something. Remember, just like up here we simplified our fraction, this is a simplified ratio. So I don't know what factor it's been simplified. My next longer side, or the medium side, is 5 times that same number, and my longest side is 6 times that same number. So I could have a 3, 5, 6 triangle, or it could be a scale factor of 3. So then it'd be 9, 15, 18. Okay? But we're given more information. The perimeter of the triangle is 98 inches. So if I start at a point and I go all the way around the triangle, it would be 98 inches. So what is the length of the longest side? Well, first we need to find out what x is. And the way we can do that is by setting up our equation in terms of x. So if I started here, I would do 3x plus 5x plus 6x equals 98. And that's because I have a triangle, and I know the relationship of the sides of the triangle, but I don't know the lengths of those sides. So 3 plus 5 is 8, plus 6 is 14x equals 98. Divide by 14, and x equals 7. Okay, but we weren't looking for x, we're looking for the longest side. Well, our longest side is going to be the one with the highest ratio value, so that's going to be 6x. 6 times 7 is 42, and our unit here is inches. Inches. Let's look at the next one. This is a property, so this isn't an example per se, but this is something that happens for all proportions. There's multiple ways that we can write this. So if I'm looking at a proportion a over b equals c over d, what that tells me is that a is related to b, but a is also related to c. So a couple ways that we can write this, not to solve for it, but just rewrite it. We can flip or reciprocate each of these fractions. We can say that b over a equals d over c. Okay, so if I reciprocate both sides, they'll still be equal. The other thing we can do is kind of taking this ratio and turning it. So it's going to be a over c equals b over d. Now, the reason we can do that is because this relationship, a over b equals c over d, also works if we turn it sideways. A over c equals b over d. Okay, and we'll see some examples of why we can do that, but the algebraic way that we can see this is if we cross multiply, this would be that bc equals ad. This will also be that ad equals bc. So with the symmetric property, we can prove that these are all equivalent ratios. Let's look at an example. So I'm going to draw a diagram for this example. It's going to be a triangle with another segment. I don't know that that's a mid-segment or anything about it, but we have these lengths, x, 6, y, and 7. And we are given the information that x over 6 equals y over 7. And we want to rewrite the proportion to get x over y equals something. Well, if I look at this ratio, or the proportion that I was given, and I look at turning it on its side, we would get that x over y equals 6 over 7. Now, why is this all important? It's important so that we can apply it to polygons. Because for congruent polygons, they have the same angles and the same sides, right? All of the measurements were equal to each other. For similar polygons, we will still have the same angles, but now we have sides that are different, and they're different in a very special way. Okay, the two polygons are only similar if the corresponding angles are congruent. So again, the angles stay the same measurements, but the sides are proportional. So what does that mean? Think about if I have a small triangle and I wanted to find a similar triangle, I could multiply it by 2. So if you think about, like, if you have an image on a document and when you put the image into the document, it's too big, and so you scale it down, but you don't want it to get distorted, you want it to stay the same image, you just make it smaller, that would be a similar image. Okay, it's not the same measurements anymore, so it's not congruent, but we're making it have the same angles, we're not making it stretched out in any direction. So for polygons, what that looks like is we can have quadrilaterals here, A, B, C, D, and G, H, I, J. And then we can know from this similarity statement, notice it doesn't have an equal sign anymore. This means similar, not congruent, which was with an equal sign underneath it. Okay, so similar is just it's called a tilde, the little squiggle. So how do we know how to write our similarity statements now? Well, we're going to, again, use corresponding angles. So I have angle A here is the right angle, and if they're not colored, you can say it's the right angle that's next to the angle with 2 congruence marks. And so I'm looking on this diagram for the right angle next to 2 congruence marks, and that's G. Angle B is the other right angle, so that's H. C has one congruence mark, that's I. And D has two congruence marks, so that's J. So again, we're writing each corresponding piece by looking at the congruence marks. Now, for side lengths, we don't have congruences, so I can't mark congruences on my diagram here. However, I can use colors to make it easier to see where corresponding sides are. So for example, I can say AB is between the two right angles, then GH is between the two right angles. So I'll call this GH is what I would set up with my ratio. The two corresponding sides are in the ratio together. And then I'm looking at BC. So here is the right angle to one congruence mark. Right angle to one congruence mark is HI. Next, I have 1 to 2 congruence marks. 1 to 2 congruence marks is IJ. And the last one, we have GJ and AD. Now, all of these ratios should be set up. I don't need all four in order to solve this, right? If I'm trying to solve for a variable, I would just pick the two that I need, and we'll see some examples of that. So let's look at an example of just finding out if these are similar. Okay, so we are given the similarity statement. We want to set up all of our corresponding sides and angles. Let's start by looking at the angles, because just like with congruent triangles, the angles are already listed in order. So we can say angle M is congruent to angle first letter, S. Angle N is congruent to second letter, angle R. And angle P is congruent to angle T. And then we have our side lengths. So again, I'm going to take my colors out. I'm going to say M to N should be S to R. And then we have N to P corresponds to R to T. So to set up my proportions here, we'll start with orange. Mn over SR. And I'm going to highlight the fraction sign just so I can represent. That's the orange side. Equals NP over RT. That's my yellow side. And the last corresponding sides are PM over TS. So what these ratios give us, each ratio gives us what's called a scale factor. A scale factor is the ratio of the corresponding measurements in the two similar figures. So what does that mean? It means if I take one of the figures and one of those corresponding sides, I should be able to find the number that I need to multiply in order to get the other figure's corresponding side. So in this case, we have an equilateral triangle. That makes it nice because it doesn't matter which side I choose, they all have the same length. But to demonstrate this, we're going to choose specifically AB to FE. And the question is, what do I have to take AB and multiply it by in order to get FE? And that's the scale factor. What do I multiply AB by in order to get FE? So we're going to set up an equation. AB times what equals FE? Well, AB is 9. I don't know what I need to multiply it by in order to get 15. So X will be my scale factor. Divide both sides by 9. Simplifying my fraction here, I can simplify by 3, so I get 5/3. Now, saying that these two figures are similar means that every side should have the exact same scale factor. Because when you enlarge a picture, for example, you want to keep all of the sides growing by the same amount, otherwise it will get stretched, it will get distorted. And so once I find the scale factor of one side, if I know that the two figures are similar, that will be the scale factor for the entire shape. But this one's going backwards, so not 5/3. Going backwards, I would have to multiply it by the opposite number, the opposite being the reciprocal. This would be 3/5. What we'd like to do is determine if the polygons are similar. If they are, then find the scale factor. So first, I would verify angles, because angles are a little bit easier to verify than side lengths. So we're going to say, does it have all angles corresponding? So does it have 3 pairs of congruent angles? I'm going to start in alphabetical order. A, B, C. A has 2 congruence marks. So I go over here and I say which angle has 2 congruence marks. That's D. B has 3. E has 3. C has 1. F has 1. So I have 3 pairs of corresponding angles. Then we also need to check that the sides correspond, meaning that they all have the same ratio. So again, using my colors, I'm going to say AB with DE. So that's 12 over 15. Simplify by 3, that gives us 4/5. The next pair of sides, BC with EF. That's 16 over 20, simplifying by 4. That gives us 4/5. So far, so good. They're equal to each other. And then the last remaining pair of sides, AC is 8, DF is 10. Simplifying by 2, that's 4/5. All 3 of those are equal, and therefore these are, yes, similar. So for our similarity statement, I like to use the angle statement that we did and just write them in order: A, B, C, D, E, F. So we have triangle A, B, C, triangle D, E, F. Again, it's very important the order that you write those vertices, just like when we were doing our congruence statements. In the next example, we're given quadrilaterals. So again, we want to find corresponding angles. This time, let's go with the number of tick marks that there are. So this is angle M. 1 tick mark goes with angle W. 2 tick marks is angle J. So that goes with angle T. My right angle is angle K. Goes with angle U. Once you've started going in a certain direction, they should both follow that same direction. And then we have angle L and angle B. And for our sides, here we have JK and TU, KL and UV, and LM with VW. My fourth side is the one without a color. So JK is 12 over TU is 6. That reduces to 2. KL is 24 over UV is 16, which does not equal 2. It doesn't really matter what it simplifies to. What matters is that it's not equal to the other scale factor that we had. Therefore, these are not similar. I don't have to continue working because I already know those won't be equal, therefore they are not similar. For number 3, we're given 2 shapes. They've got right angles, they're 4 right angles, so we know that they're rectangles. Now this time, it's going to be harder to match up angles because they're rectangles, but we also know that rectangles have a lot of similarities already, right? It's got opposite sides are congruent, opposite sides are congruent. So we have a lot of information here. So because of all of these symmetries of a rectangle, instead of comparing all of the angles, what I'm going to do is compare the sides. And I'm going to say small to large. So I'm going to compare and see if they give me the same ratio. So small side to small side, that's 10 to 15. 15 is smaller. Reduced by 5, that's 2/3. The larger sides, that gives me 15 to 20. Reduce that by 5 would give me 3/4. These are not equal, so they are not similar. If these had been similar, there's a lot of different ways we can name it. What I would do is pick a vertex, for example, K and W, and then just make sure that your next angle is along a small side, then you go along a small side, and then you just name them in order. Number 4. Here we have two pentagons, 5 sides pentagon. Okay, so I'm going to start by listing the angles. I'll start with angle E, corresponds with the other angle with 2 congruence marks, that's angle T. And then angle A goes with 1 congruence mark, and now it doesn't matter if I go with S or U, but whichever way I go, I'm going to keep going in that same direction. So that I can make them both go clockwise, I'm going to go with angle U. Then we get angle B is a right angle, clockwise, continue to angle V. Angle C, continuing clockwise, is angle R. And angle D, continuing clockwise, is angle S. Now, as we saw when I demonstrated with example 3, they don't always have to both go clockwise or both go counterclockwise. It could be that their angles are named in opposite directions, that's fine. But that's just because I have this symmetry, right? There's this like line of symmetry that I could fold this shape in half. So I had a choice of which direction to go, and I could have used either one. Okay, so that's the angles. Now we need the sides. So I'm going to, again, using colors, say EA to TU. And then I have AB to UV, BC to VR, and CBRS. So I'm going to start with orange. That's AE to TU. That's 12 over 6 equals 2. The next sides I'll compare. I'll say AB to UV. That's 18 over 9 is 2. Then BC to VR. 18 over 9 is 2. If you notice, it's the same numbers repeating. This is also going to be the same ratio as CD to RS. And then my last side, which is DE to ST, that's the same values as our first calculation, DE to ST. And so we say this does work. We can say the scale factor is 2. And we can say, again, I'm going to just name them in the same order that I listed those angles. EABCD is similar to TUVRS. So that's recognizing when two shapes are similar. How can we prove that two shapes are similar? So how much information do I need in order to say that they're similar? So right now, we would need all of the angles and all of the sides in order to say that. But just like with congruences, there are some shortcuts. Okay, so if we're missing some information, we can use this idea of scale factor in order to find the missing pieces. So if we're looking for the scale factor from DE to DA, so again, that's saying DE times what equals DA. So 6 times what is 9, divide by 6, simplifying by 3, that would be 3 halves. So then what is the scale factor from EFGD to ABCD? Well, from our little to our big, it's growing, so it should be a scale factor bigger than 1. EFGD had the same side as DE, so I can use the calculation from above, 3 halves. What about backwards? Well, if I'm going from ABCD to EFGD, then I need a side from ABCD, so DA is an example, to DE. That's going to be my equation backwards. So that's 9 times x equals 6, divide by 9, x equals 2/3. 2/3 is smaller than 1, so that means that the shape is getting smaller. From ABCD, it gets smaller to EFGD, right? From EFGD to ABCD, it should be getting bigger. EFGD to ABCD, it does get bigger. And you could have chosen any 2 sides from those quadrilaterals. I just chose the ones that we had already used. Okay, but we also want to find x and y. So in order to find x and y, what we're going to do is we're going to set up proportions. And I usually start by saying, what do I need to find? So if we're finding x first, then I say, okay, FG That's what we're looking for, over what does it correspond to? FG corresponds to BC. And then which pair of sides do we have all the information for? So I can't pick these ones because there's a variable. I can't pick these ones because there's no information there. So I'm going to choose the ones that I have all of the information for. I started with FG, so within that same quadrilateral is ED over BC and AD. So that's X over 7.5 equals 6 over 9. Multiply both sides by 7.5. X equals 5. We'll do the same thing to solve for Y. So solving for Y, I'm going to start with what don't I know. I don't know EF corresponds to AB. What pair of sides do I know everything for? That's these two sides over here. So that's EF is in the same quadrilateral as EB over AD, which is 9. Again, multiply both sides by 5. We get that Y equals 30 divided by 9, which simplifies to 10/3, or we can write that as 3 1/3, 3.33 repeating. Now, if it does not say to rewrite it as a fraction or as a decimal, you would leave it as a fraction, because this is not an exact decimal. We rounded that decimal. Okay, there's no way to put that in as an exact number. So if it doesn't specifically say to give it in decimal form, you have to leave it in fraction form. Okay, let's look at our last example for this section. In this example, we want to solve for X using our algebraic methods that we hopefully remember. If you need a refresher, I'd be happy to go through this in more detail with you during office hours. So we're solving for X. The first thing I'm going to do is cross multiply, which means multiplying by the denominators. So I'm going to multiply here. And remember, division is a grouping symbol, so you might want to add parentheses around your numerators and denominators that have more than one term. So if there's any pluses or minuses in your fraction, put parentheses around it. So we have X plus 5 times the quantity of X minus 6 equals 3 times 4, which is 12. To multiply this, we need to FOIL, which is distributing. So we have X times X, which is X squared, X times 6, which is minus 6X, plus 5X minus 30 equals 12. Combine like terms, negative 6 plus 5, X squared minus 1X minus 30 equals 12. Minus 12 from both sides. So we get X squared minus X minus 42 equals 0. So why did I subtract the 12? Because if I have an X squared, I need to set it equal to 0. And why do I need to set it equal to 0? Because in order to solve for X, we need to factor. So remember, anytime you have a degree higher than 1, so if I have a variable with an exponent, I need to set it equal to 0 and then factor. So how do I factor this? Well, we're looking at, if we use the X method, we're looking for two numbers that multiply to negative 42 and add to negative 1. So we need to look at factors of 42. I like to make a factor list, not a factor tree, but a factor list, meaning I'm going to list all of the possible factors of 42. That's 1 times 42, 2 times 21, 3 times 14, 4 doesn't go in evenly, 5 doesn't go in evenly, 6 times 7, and there's the winner, because those are 1 apart from each other. So 6 and 7, the bigger one has to be negative. What does that mean? Well, it means that I can rewrite this polynomial as x plus 6 times x minus 7 equals 0. And then because it's equal to 0 and it only works for 0, doesn't work for any other number, I can set each of those factors to 0. X plus 6 equals 0 and x minus 7 equals 0. Solving for x now, subtract 6 from both sides. X equals negative 6 plus 7, x equals 7. So I have two options for what x can be. X can equal negative 6 or 7. Okay, why can x equal two different things? Well, because we have two variables here for x, the way that they interact means that I could use either value. Now, x is not a length. If I knew that x was a length, then it would have to be the positive one. But in this case, I don't know what x represents, and therefore it could equal either of those two values. Okay, let's take a look at 7.3. In 7.3, we're looking at what are those shortcuts that we can use for similarities? What's the minimum that we need to know in order to use proportions to finish solving for similar sides or similar shapes? So our objective here is to use the angle-angle postulate, side-angle-side similarity, and side-side-side similarity theorems, and also to use similarity to find indirect measurements. So remember, we were just talking about how similar polygons have corresponding sides that are proportional, not equal. If the sides are equal, then that would be a congruent shape. But we're talking about similar shapes. So we can solve for these missing sides by setting up proportions. What is the same as what we did last chapter is that corresponding angles are still congruent. So if I have these two shapes, I have two triangles here, and I know that they're similar, and I want to find the missing part. So I like to start with the angles again. I'm going to start with angle Y has to be congruent A and P, A and P. So angle A congruent to angle P, then Y has to equal 31. Okay, our second variable here is X, and it's for a side length. I like to start with my unknown side, so that's QP over which side corresponds. Well, QP is the first two letters, so I'm looking here for the first two letters is BA. And that has to be equal to, and I'm going to look for the pair of sides that I know all the information for. So these sides are the ones I know all the information for. And that's QR. QP is in the numerator, then QR, same triangle in the numerator. QR. QR was the second two letters, so the second two letters is BC. BC. Notice how I'm always going back to that similarity statement to make sure that I'm using corresponding sides, not just by what the diagram shows me, not my assumed from the visual diagram, but actually from the statement. So now I can fill in values. QP is X over BA is 14. QR is 9. BC is 6. Solving for X, I'm going to multiply both sides by 14. And X equals 21. In our next example, we have two rectangles. I'm telling you that these are rectangles. And what we know then is that opposite sides are congruent. So this is 12, this is 8, this is X, and this is 12. Okay, so remember the last example that we had with rectangles. This time we know that they're similar, so we're going to compare small side, because the two small sides are congruent, to larger side. So we're going to say small and larger. So my small side, that's 8, over my small side here is X. Larger side, that's, sorry. The small side on this one is actually 12, not X. Over 12. And then the larger side here is 12 over the larger side here is X. So solving for X, I will cross multiply. 8X equals 144. Divide by 8. X equals 9. So again, small was 8. Small here is 12. And then the larger side here is 12, and the larger side here is X. For example 3, we're comparing the two triangles here, LMN and PQR. I'm going to start by solving for X. So I'll put the unknown on top, starting with QR. X over, and which side corresponds with QR? Let's use colors. QR corresponds with MN. I know I'll need to find PR, so PR, first last is LN. So I have X over 15 equals, Now, I don't want to use the yellow ones because that doesn't give me all of the information I need to solve this. I want to use the sides that I know everything for. And so that's going to be the sides without a color here. I took x from this triangle, so my numerator needs to come from the same triangle, 12 over. My denominator comes from this triangle, so the denominator comes from that same triangle, 9, times 15 times 15, x equals 12 times 15 divided by 9 is 20. And then a separate proportion to solve for y. I'll put my unknown in the numerator. Y over 21 equals, from the same triangle as y, 12 over, same triangle as 21, 9. Times 21 times 21, y equals 12 times 21 divided by 9 is 28. For the next set of examples, we're doing the same thing. I'd like you to try this on your own as a try this, and I'll have you put your answers into Edpuzzle and we'll go over it during class. So what postulates can we use? What are the shortcuts that we can use in order to, the minimum that we need to have in order to say that two shapes are similar? Well, for triangles, we can use angle-angle similarity. And what that means is that I have two congruent angles, then the triangles must be similar. Now, if I also have a side, if I have two angles and a side, and those sides are congruent, that would be a congruence statement. But this time, we're not looking for anything doesn't need to have a side because we're looking at similarities. So we need less information than we normally would for a congruence. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. So in this example, we have SRT congruent to 1, 2, no marks, 1, 2, no marks, MLP. Let's look at some other properties that we know from the previous information we've seen. So in order to use the angle-angle similarity, we need to be able to get two congruent angles. So what are some ways that we can get two congruent angles? Well, we know we have the reflexive property, which we used pretty frequently for sides, and we used it a few times for angles. Notice this is actually two triangles here. We have our triangle BAD, and we have our triangle CEA. And both of those triangles contain this angle A. It's the same angle, so they must be congruent. We also know that all right angles are congruent. So angle B must be congruent to angle S because they're right angles and equal to 90-degree measurements. We know that if we have an angle bisector, it gives us two congruent angles. So that is angle GHI and IHK, or JHK if we're looking at it within the triangle. We have vertical angles that are always congruent. That's LPM and OPN. We know that parallel lines give us alternate interior angles. So again, I'm going to use the Z method. So we know that that gives us alternate interior angles here. Angle B is congruent to angle ECB. And it also gives us congruent angles if we have diagonals this way. We have two pairs of congruent angles. So we have angle G congruent to angle H. We also have angle F congruent to angle I. And then we have parallel lines that give us corresponding angles. So for this diagram, if I draw the Z, it would go off in the opposite direction as the triangle. And so I don't need alternate interior angles for this one. I need corresponding angles, giving me angle KML congruent to angle N. And then we can apply that same thing to these pairs of parallel angles here. We have parallel lines and this transversal. We also can say that these same parallel lines with this transversal. And so we have corresponding angles here, angle J with angle G, and I with angle H. So let's see if we can determine which of these diagrams have enough information. In our first example here, we have a 90-degree angle given. We know those are congruent. We also have vertical angles given. And so we know that CAL is congruent to the angle with no mark, which is H, 90 degree, which is I, and 1 hash mark, which is L. For our second diagram here, for a second example, we have 75 degrees. I don't know what the measurement of angle Q is. Is it 75 degrees? How do we tell? 180 minus 61 minus 44, which does actually equal 75 degrees. And so we have 75 degrees and 44 degrees match. So angle C, which is 44, corresponds with angle R. B, 75 Q, and A is the one that's left over with P. On example 3, we have a right angle here. We want to know, is angle F also 67? So that's 180 minus 90 minus 22 gives us 67. And therefore, these do have corresponding angles that are congruent. Angle B is my right angle with E. C is 67 with F. And A matches with D. I'd like you to do these two as a try this, and we'll go over them in class. Make sure you're thinking critically about the examples we've already talked about, and don't assume any information other than that lines are straight. Continuing with the examples on the next page, we want to determine if the triangles are similar, and if so, write the similarity statement. So I'm going to look. In example 1, we have parallel lines. Here are my parallel lines, transversal between them. I'm not drawing a Z because I can see that I'm not going to be using alternate interior angles. I'm using corresponding angles here. And so I can see that I do have two angles that match. So we can say E with C, A with D, and D with B. For this next one, we have the 45 angles match. 68 and 67 do not match, but we still need to check. Maybe T is 68. So we do 180 minus 67 minus 45, and that gives us 68 degrees. So remember, as soon as you have two angles, you can always find the third. And now I do see that these angles are congruent to each other. So K with R, L with T, and M with S. And then we have this diagram, and remember, this gives us two pairs of congruent corresponding angles. And so we have L with L, Q with M, and R with N. Our second way that we can tell when two triangles are similar is using side angle side, but this time it's a similarity theorem. So instead of looking for all of our measurements to be equal to each other, we're looking for the sides to be proportional to each other. So when we're looking for side angle side, we're looking for one angle of a triangle to be congruent, and the two sides that are touching that angle, the two sides adjacent to that angle, are proportional. Okay, so if we're looking here, we have the red side, that's AB, has to be proportional with QR at the same ratio as AC to QS. And notice again, my numerators came from the same triangle, my denominators came from the same triangle. The angles that have to match are the angles that are between the sides that are congruent, so that's angle A with angle Q. And so our triangle similarity statement, if I start with angle A, B, C, the angle that goes with A is Q, go along the red side, so that gives us QRS. This is not the same as if I said this was QSR. Very different statement. Let's see if we can use it. In this example, we want to show that only one pair of the triangles below is similar. We're using SAS theorem, so we're going to solve both of them, but only one of them should actually be similar. So let's start with number 1. We have our matching angles. Angle P is congruent to angle A. First step, matched. Then the two sides have to be proportional. And so I'm going to say small and larger. Because I have nothing to say if AN should correspond with PM or PR. But the two smaller sides should correspond. So here I have AN and I'll do AD over, from the other triangle, smaller side is PM and PR. AN is 6, PM is 6, AD is 8 over 10. Are those two things equal? Absolutely not. This one is 1, that one is smaller than 1, so these are not similar. For number 2, again, we have angles first. Angle G corresponds with, is congruent to angle E. That works. And then we have our sides. And again, I'm going to compare small side to the larger side. So here, if I say the smaller side is AG and GU is the larger one, here my smaller side is BE and EF is the larger one. So that gives me 12 over 15, and I want to compare that to 16 over 20. Well, 12 over 15 can reduce by 3, leaving 4/5. And this also reduces by 4 this time to 4/5. Those are equal. And so this is similar. So which vertex corresponds with U? Well, if I start from my given angle, this is the larger side. So from the given angle, the larger side is EF. So which angle corresponds with U has to be the one from the orange side. So it's going to be F, G is the given angle, and A is the other one. So again, useful to have colors. Let's look at our last way of determining similar triangles. The last method to determine similar triangles is the side-side-side similarity theorem. So we had a side-side-side congruence theorem. This time we're looking at similarities. So we're looking at proportions of those sides. If the corresponding side lengths of two triangles have the same ratio, then the triangles are similar. So what we're looking at is comparing red to red, blue to blue, purple to purple. Now, in a standard problem, it's not going to be color-coded like this. So the way that I think about this is small, medium, larger. Okay, so for our purposes, and we'll use highlighters to continue marking our sides, our corresponding sides. We have AB with QR, we have BC with RS, and we have CA with SQ. And that will give us triangle ABC. A is between red and blue, so we go between red and blue is Q. Red and purple, purple and blue, purple and blue. I am going to recommend that you use colors. So let's look at our examples. We want to show that only one of these is similar by using SSS. Now, I'm not going to put in the place for you to put it in Edpuzzle yet, but I'm going to have you do this on your own. Instead, I'm going to show you an example, and then I'll put in where you can put your answer on Edpuzzle. So let's look at example 1. Now, how do I know that I want to use SSS for this example? I'm not given any information for any of the angles. If I have no angle information, that tells me I'm going to use SSS. So how am I going to set this up? I'm going to get my colors ready first, and I'm going to highlight the small side. It's 8. Which of these is the smallest? Is 16. My middle side, this is the middle side, so that's going to be 9 and 18. And my larger side, 12 and 24. And then I'm going to write a ratio for each. So I'm going to start with my triangle ABC. That's 8, 9, 12. And then my triangle HJG. Smallest is 16, medium is 18, largest is 24. Now if I simplify that, that's 1/2. This is also 1/2. This is also 1/2. They all equal 1/2. So this is similar. Then how do I write the similarity statement? Well, angle A, orange-blue, corresponds with orange-blue is G. Angle B is orange-yellow, corresponds with H. And angle C with angle J. And how did we know that? By side-side-side similarity. Okay, so now I'm going to put in where you can Do the 2 examples from above and put your answer into Edpuzzle. For example 2, we are given an angle here, okay, but we're not given a second angle that corresponds. So what we need to do is we need to find out, is angle E also 30 degrees? We do 180 minus 90 minus 55. That gives us 25. Sorry, it gives us 35. And so that tells us that these 2 triangles are not similar by angle. For number 3, we were given 2 right angles that are similar, 2 42-degree angles that are similar. So this one is similar by AA similarity. Angle F corresponds with angle J, G with K, and H with H. Looking at our last page of examples, for number 4, here we have PM parallel to QR. If I have 2 parallel lines in a triangle, that gives me these corresponding congruent angles. I can draw the lines here. The transversals might help you start being able to see it. Okay, so N corresponds with N, M corresponds with R, and P corresponds with Q. That's by angle similarity. On number 5, we have 102 and 30. Is this 30? 180 minus 102 minus 48 equals 30. So that means these are indeed congruent, or sorry, similar, not congruent. These are similar. Angle E goes with L, F goes with M, G goes with N by angle similarity. And number 6, ABC. I'm not given any angles, so I'm going to use side, side, side. I'm going to look for, again, small, middle, and large. Smallest side here is 38. Smallest side here is 30. Medium is 42 and 35. And largest, 54 and 45. A, orange blue is Q. Sorry, I should see if they're similar first. So small, starting with ABC, we'll do 38, 42, 54, 30, 35, 45. If we reduce this, 38 over 30 reduces to 19 over 15. 42 over 35 reduces to 6/5. These are not the same. And therefore, these are not similar because of side, side, side. Okay. I don't have to check the third one because as soon as 2 of them don't have the same ratio, it doesn't matter if the third matches one of them, they can't be similar. Okay, and then our last 2 examples here are using similar triangles in order to find a missing side. So what I'm going to do is looking at this triangle, how do we know that it's similar? Well, we have an angle. We should be able to find a second angle. By vertical angles, we have that. And so I can say that the side between angle with 1 and angle with 2 marks is similar to the side between 1 and 2 angle marks. And the reason it's important to mark these is because I need to be setting up my proportions with the corresponding sides. So 2 to none, 2 to none. And my third side length, 1 to none, 1 to none. So how do I set up my proportion? Well, here I have my blue side and my orange side need to be in the proportions because my yellow side does not have one of the side lengths. So it's missing information that I would need. And therefore, I'm going to set up my proportions with blue and orange. So from the same triangle, I'll set up blue over orange. So that's going to be x over 9 equals blue over orange, 8 over 2x. Cross multiply, 2x squared equals 72. Divide by 2, x equals 36. Sorry, x squared equals 36. Well, how do I find x? What number when squared gives me 36? So you can think about as the square root property, which says that x equals plus or minus 6. What that means is that x could be 6 or negative 6, but this time we do know that x is a length. It's a side of a triangle. Side length must be positive. Therefore, x equals 6. And our second example here, we have parallel lines, so we have corresponding angles there. Because of the way this is set up, I'm going to be looking at different side lengths from within the same segment, and so I'm going to redraw this with my two triangles. 1, 2, 1, 2. Small triangle, I've got 10, x plus 2. My larger triangle, I have x plus 14. But this side length is this whole length here. So it's not x, but it's x plus 10. Between 1 and 2, congruence marks. Next to 1 congruence mark. Next to 2 congruence marks. So in order to set this up, again, I don't want to use the yellow side because the yellow side doesn't have enough information. So I will set this up blue over orange again. And so we have 10 over x plus 2 equals, for my second triangle, blue over orange, x plus 10 over x plus 14. I have plus signs, so I'm going to group, cross multiply. 10 times x plus 14 equals x plus 2 times x plus 10. Distribute. 10x plus 140 equals FOIL x squared plus 10x plus 2x plus 20. Collect like terms. 10x plus 140 equals x squared plus 12x plus 20 minus 10x minus 140. Why am I subtracting? Because I have that x squared. Minus 10x minus 140. 0 equals x squared plus 2x minus 120. So I need to find two numbers that multiply to negative 120 and add to 2. Again, I'm going to do a factor list. 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 24, 6 times 20, no 7, 8 times 15. I'm looking for it to have a difference of 2. 9 does not work. 10 times 12 works. 10 and 12. The bigger one should be positive. So this is negative 10 and positive 12. 0 equals x minus 10 times x plus 12. Set each one equal to 0, and it only works for 0. It would not work if that had equaled 5 or 1 or 7 or 3. It has to equal 0. 0 equals x minus 10 plus 10. 10 equals x. 0 equals x plus 12 minus 12. Negative 12 equals x. Here we have that x is a length, right? X is a length here, so it cannot be negative, and so x equals 10. If you can find those two factors without a factor list, by all means, you don't need to draw out your factor list, but I'm showing you this because it is a surefire way to always find out if you can factor a polynomial. Again, if you have questions or you want some more examples on that, I would be happy to go through that with you during office hours.